Good afternoon, everyone. We'll get our program started. I'm Allison McKay. I'm the chair of the Civil, Environmental, and Geodetic Engineering Department, and it is my pleasure to welcome our distinguished speaker, Dr. McCartney, as well as students and all of the friends of Ohio State who are gathering here with us today for the 2025 T.H. Wu Lecture. And when I think about the T.H. Wu Lecture, there's two themes that really come to mind. The first is community. And so this continues to extend the tradition that Professor Wu brought with him both at Ohio State through his research group, which I know from speaking with alums have led to some really enduring friendships over many, many years since students spent time in the department, but also the folks that he met throughout the engineering community and many other communities from his wide range of interests outside of engineering. So we sometimes forget that we all have interests that are beyond just engineering, and he certainly was true to that. And the other exciting thing today about our talk is just really the interdisciplinary aspect of it, and how do we leverage Earth resources and think about impacts of environment on the work that we do. And I think of some of the work that T.H. Wu did, leading some initial initiatives to think about bio-inspired slope design. How do you integrate trees into an engineered system and take advantage of those properties that the Earth gives to us through the ecological function of trees. And so we'll also hear today about a much more integrated perspective of how we can think about doing engineering design. So I am very excited about that, and I'm pleased now to turn things over to Professor Patrick Basal, who has really been a key host to all of the events of today.
Thank you, Allison, and thanks all for being here. We're looking forward to Professor John McCartney's talk and today's T.H. Wu lecture. I first wanted to share a few announcements about our geotechnical program. First and foremost, Professor Daniel Pradell officially transitioned from his role as Professor of Practice to Emeritus Professor. So I just wanted to have a round of applause for And so for those of you who don't know, Daniel did help to start a lot of initiatives for our geotech program, including building up the geotech undergraduate course, like the lab course, and also starting up some new graduate classes and other initiatives. So we're really grateful for everything he's done, and we only hope to be able to continue his legacy moving forward. We'll try our best, but I'm not sure if we can do it the same way. And another big news item, Assistant Professor Martina Lavini, who's here with us today, joined our department with expertise in geoenergy systems. And so we're excited to have her as part of our group. Also, the families of Dr. Min Lu and myself, we both welcomed newborns just this past December. They're actually born only 4 days apart, so we're looking forward to future play dates with our kids. And actually, Martina is also expecting in about a month, I believe, so coming up. And our CTL Geotech Research Lab recently obtained, under Dr. Min Lu, she was able to obtain an environmental triaxial testing system for her research on permafrost degradation and hydrate dissociation. So that's now up and running, and I think you're starting to get some initial tests going. So. In other news, the Geotechnical Lab course continues to support our undergraduate students, and each semester we're seeing a lot of enrollment, and we're hoping for continued high enrollment in future semesters. And we're thrilled to also share that Rudy Frizzy, who's here with us today, and his wife Susan, Rudy's an alumni of Ohio State. They formally established 2 endowments to support the future of geotechnical engineering here at Ohio State. One is an endowed scholarship fund for students interested in pursuing a career in geotechnical engineering, and the other one supports geotechnical research, providing faculty and graduate students support as well. And we're beyond grateful. We're very appreciative of this investment, which will ensure that our program continues to thrive. And we'd like to take a moment to thank Rudy and Susan for their incredible support. And at this time, I'd like to invite Rudy up to say a few words.
Okay, thank you, Patrick. Full disclosure, Susan and I are not expecting, so that's okay. The other thing I get, coming back to campus, which is exciting, that doesn't really change, is the lecturers in the front and all the listeners are in the back. So feel free to move up for the presentation. This is really a cool lecture for me because I had the opportunity to work with Tien H when I was an undergraduate student. And, we're all somewhere because of what somebody else does for us. And, I was just an undergrad student and I was keen just to understand what geotechnical engineering really was. And Tien H was kind enough to allow me to accompany one of his PhD students on a slope project in Southeast Ohio. So I think things were a lot simpler then. There weren't as many forms that had to be signed that could let the students go do things, but just a great individual, and I am where I am because of him helping me in those opportunities. So Susan and I are really excited about being able to do something like this, and I really encourage students, be aware of this. This is something that is in place to help students. It's in place to help researchers. And we're always looking for really good ideas to help, elevate the practice, but also elevate the university here as well and the initiatives that are happening out of here. So, and for the folks that are in the room, folks like myself, just think back. You are where you are because of what somebody else did. And Susan and I see this as an opportunity to help pay it forward, and I encourage others to do the same. So I'm really looking forward to the lecture today, and thanks again for everything that you're doing. Appreciate it.
Let's have Daniel Pradell up to say a few words about THU.
I'm really also excited about the lecture today. And I'm supposed to be retired, but as you can see, they make me work once in a while. For me, my first 4 years here at Ohio State, the highlight was always to see Tien H. He and I would often go for lunch together. And I had the privilege of many of his former students knew that he would come to campus on Fridays, also sometimes on Tuesdays. And so I got to meet Richard, Peter, CK, and many others here on campus. And it was really every week or every year, that was really the highlight of my days here at Ohio State. For people of my generation, Tien H was a mentor through his books. People in geotechnical engineering up to the 1950s, we had very few books that were available, and many of them were really complicated. They were what I would call graduate level books. And his soil mechanics books that he published in the mid-1960s was really the first, in my opinion, simple, easy to understand a book, and therefore he really mentored many generations in the field or introduced them to the field of geotechnical engineering. He came to the US in 1947 from China, graduated one of the first PhDs with Ralph Peck. And very, very quickly, he moved into probabilistic risk analysis and also into the area later on of biotechnical slope remediation. And during the past few months, I was able to go through many of his, what he called PowerPoints, which of course were 35 millimeter slides. And I was amazed at how they were all, well, not all, but the majority were handwritten very, very clearly, detailing a lot of them on probabilistic methods. very clearly explaining his research and methodology. And today, he's probably best known for his Bayesian decision analysis and the field that many people today call georisk. There are conferences held on a routine basis. This is one that I attended in Taiwan in 2019, where he was really honored, and everybody recognized that he was at the origin of what we sometimes also call geotechnical reliability. I loved, his very simple 35 millimeter slides, almost all of them black and white, hand drawn, clearly showing the effect of groundwater, clearly showing the effect on stresses, and also how thorough he was. He would look at the effect of wind, for example, on the trees, the effect of reinforcement, the effect of changing angle of the roots as they're being pulled, and in many areas, in many other areas, he also had significant contributions. He spent several months in Antarctica and wrote papers and contributed to the field of glaciology. Through his life, I was able to see that he worked on areas that I did not expect him to work on, like, for example, offshore platforms. But also he had a keen interest in the emerging field in the 1970s of soil dynamics, what later became geotechnical earthquake engineering. He wrote in 1975 a well-known and seminal book called Soil Dynamics, and a lot of those pictures that he had involved, for example, the San Fernando Dam failure in 1971 in Los Angeles, the failure at Olive View Hospital, and so he had many interests, not just related to georisk or biotechnical remediation. He retired in 1994, but he remained constantly involved with the campus. Even in his 90s, he would never take the elevator. He'd go the 4 floors of Hitchcock. Okay, if you wanted to hide from Th. Wu, one student told me all you had to do was go into the elevator. I talked to him several times about his research. He was still doing research. He was still writing papers, and he was still working on the manuscript of a book. In fact, one time I remember he came to me and he said to me, Daniel, I need a genius. Okay, and that's what Th. Wu would typically call, students on campus. They were all geniuses. And I said, what do you need a student for? He says, well, I have this slope that I reinforced for ODOT many years ago, and I'd like to go and read some of the instrumentation. And of course, he was, I think, 89 at the time. So I got him, I found a good student, and I said to the student, make sure you carry everything up and down the slope, make sure that, you take all the readings, and, he's 89 years old. And so the student came back to me and I said, how did it go? And she said, he didn't let me do anything. He was up and down the whole time, up and down the whole time, taking all the readings himself. Okay, I was just there watching. So that was Th. for me. One thing that he really liked was sitting approximately where the camera is and listen to a good presentation. And he really loved these yearly meetings. He also loved one of the pictures here is at one of the GI, Geo Institute meetings here in Columbus. And by the way, talking about the Geo Institute meeting group here in Columbus, if you can stand up, okay. We're gonna meet afterwards together if you'd like to be involved, getting speakers from industry to come, and in addition to the Th. Wu meeting under the ASC Geo Institute umbrella, please meet both of us after the talk. He also loved music. In fact, he was a professional level pianist, and he's somebody that I miss dearly, but I'm glad that we are here every year to remember him. Thank you very much.
All right, so next I'm going to give a brief bio for Professor John McCartney, and then we'll get started with the lecture. John McCartney is a professor in the Department of Structural Engineering at UC San Diego, where he holds the Hal Sorenson Endowed Chair. His research interests include unsaturated soil mechanics, geosynthetics, and energy geotechnics. His research was recognized by the R.M. Quigley Award for the Canadian Geotechnical Society in 2020, the Walter Huber Civil Engineering Research Prize in 2016, the James Krause Medal from ASCE in 2012, the DFI Young Professor Award in 2012, and the NSF Faculty Career Award in 2011. He's the vice chair of the new CEGE Institute Task Force on Energy Geotechnics and is the chair of the Unsaturated Soils Committee. He's the co-editor-in-chief of Computers and Geotechnics and is on the editorial boards of several other geotechnical journals. And he received his bachelor's degrees and master's degrees from the University of Colorado Boulder, sorry about that, and a PhD degree in civil engineering from UT Austin. For those of you who attended the ACE, or for those of you who will attend the ACE GeoFrontiers Conference in Louisville next week, John McCartney is going to be giving the Shamshir Prakash Award Lecture. It's going to be on a different topic than what he's talking about here, so please be sure you attend that if you do attend the conference next week. All right, and so with that, we'll have John McCartney come up to give his talk. Oh, and hold questions until after the lecture, and after questions, we're going to have a reception in the lobby. So. Oh, and there is a sign-in sheet for PDH credits. So if you haven't received that, I think there's one maybe on every row of tables. All right.
So thank you very much. I'm very happy to be here to give this lecture, to meet new friends and also some old friends. And I'm very happy to give this presentation in honor of Th. Wu. I'll say a few words about that in a second. So my presentation today is on a topic that I've been working on for maybe 16 years or so. So I decided to make the title Past, Present, and Future. The past isn't so long ago, but I think I wanted to talk about the state of the art, things that we understand very well, some things that we're doing right now, and then some things that we potentially could do that could give us some good opportunities. So as I said, I'm very grateful to give this presentation in honor of Th. Wu. I never had the opportunity to meet with him, although I was aware of him from very early on in my education. One of the courses I took when I was an undergrad master's student at University of Colorado Boulder was on advanced geotechnical analysis, and we had to do slip line analysis, looking at bearing capacity equations for foundations. And Professor Wu's soil mechanics textbook is one of the few that has a section on that topic. There are some other ones, but I still give this section to my students when I talk about foundation engineering. So it's nice. Most people say, okay, here's your final answer, 5 times the undrained shear strength is your bearing capacity. But there's a lot of mathematics and assumptions and things that go behind that that I think was very nicely presented in his book. And maybe in the context of this presentation where we're using foundations in a way that they're not normally used, I think that Professor Wu is a pioneer in using innovative solutions in geotechnical engineering, so hopefully we can continue on with that theme in the future. Okay, so here's an overview of my presentation today. There are several different topics, but hopefully I can give you a good understanding of energy piles, how they work, why we want to use them. I'll talk about some analyses that we can use to predict the thermal and mechanical response of these, and mainly present the performance of these from 2 case histories. These are both performed back when I was a professor at University of Colorado Boulder. One at U.S. Air Force Academy, and the other in downtown Denver. One focused on the response of single piles, and then one response of energy piles under building operations. I called this the past because I think energy piles are a proven technology. I'll demonstrate that with some of the results that we have from these case histories. But there are several companies that are working together with foundation engineering and foundation contractors and mechanical contractors to integrate heat exchange and deep foundations. So these are being used in practice. You may have heard in the new Google campus, they put all of the buildings there on energy piles. So there are some high-profile projects being constructed in the US that are using this technology. Present, I wanted to talk about using energy piles in a different way than they're normally used. They're usually used for exchanging heat between a building and the ground for heating and cooling. But because these are usually closely spaced elements in the ground, we can also use them for heat storage. And in this case, you're going to heat them up to higher temperatures than you'd expect in the past. And there are some interesting things that could happen there. And finally, for the future, I wanted to talk about ways that we can use heat to improve the behavior of soils. And we'll talk about how this can work. We call this thermal soil improvement. So one of the main motivators for my research is just a high energy use by buildings. This is a survey from the EIA in 2018. I looked, and this is still the most recent version of this. But buildings use 40% of our energy, 70% of our electricity, and 53% of our natural gas. And that leads to a lot of carbon emissions. So if we can use some strategies to reduce these through high efficiency technologies like geothermal heat exchange, it's a positive. I also wanted to talk a little bit about thermal energy in urban areas and some of the questions that we have. So we need heat for our buildings, so how can we obtain that thermal energy sustainably? Energy piles are the strategy I'm going to talk about today. But we also have a lot of thermal energy coming from the sun. And are there ways that we can harvest that heat and inject that into the ground to store the heat? There are some opportunities there, and energy piles are a good way to do that. There are some risks if everybody adopts energy piles and every building has them. Potentially we could have waste issues. So we need to make sure that if we're rejecting a lot of heat to the ground, that we're not contributing to the urban heat island effect. But energy piles are a good way to move heat from one place to another, so there could be some strategies to take care of that. But that waste energy could also be a resource, so we could use that to achieve other purposes, as I'll talk about in a second. So those are all, thermal energy comes from the sun usually, but the subsurface can play a key role in handling this. So the subsurface is usually a good insulator. Soil has a mixture of air and water, and air is a very low thermal conductivity material, so it acts as an insulating material. The subsurface naturally stores heat. Usually when we look at the ground profile, we see a profile that looks like this, where you have fluctuations in the ground temperature in the first 5 meters. And then if you go below that, you approach the mean annual air temperature. Heat transfer in soils can occur due to both conduction as well as pore fluid movement. So if we have saturated soils, we could have groundwater flow that could take the heat away. If we have unsaturated soils, you don't have that groundwater flow, so there's kind of more of a insulating effect, but you could have phase change, and that could lead to some interesting effects. And mainly, geotechnical engineers, which is what we are, what I am, we're installing structures in the subsurface that we could be using for multiple purposes to transfer thermal energy. So I've been trying to categorize thermal energy into 3 different categories. Thermal energy is a resource, so we can use this to transfer it to and from the ground to our building for space conditioning and displace technologies that may rely on burning fossil fuels. Thermal energy could be a waste, where if we inject a lot of heat in the ground, we could affect neighbors and potentially reduce the efficiency of other geothermal systems. And we know that in many urban areas, infrastructure could also be releasing heat into the subsurface. But there are many ways that we can use that heat in engineering as a tool. Whenever there's a problem, we always need to think of an opportunity. So I'm going to talk about kind of two of them in this presentation today. The first is the improvement of saturated clays using thermal consolidation. And the second is using thermal drying to enhance the behavior of unsaturated compacted soils. There's other opportunities, modifying landfill processes, de-icing bridges, remediating contaminated ground that I'm not going to talk about today, but are other potential ideas. Okay, so one of the main tools that we're going to be using in energy piles is this concept of a ground source heat pump. When you think of geothermal energy, you're not necessarily generating energy. You're moving it from one place to another. And the heat pump is the tool that we're going to be using to do that. We have two different loops, one in the ground, we call that the ground loop, and then we have our refrigerant loop. Three, if you want to consider the system that is distributing the heat to your building. The refrigerant has a refrigerant that is going to exchange heat as it's going to change phase as it expands and contracts. And we're going to be using that to extract heat from the loop that's going in the ground. So when we want to heat our building, we're going to inject heat into the ground and extract, or we're going to put cold water into the ground and hot water is going to come back. And the refrigerant, we're used to using these in our conventional air source heat pumps that we have for air conditioning purposes. Excuse me. But when we have an air conditioner, it's probably 40 Celsius outside, and we want our house to be 20 Celsius. So we have to reject heat at a much higher temperature so that we have a heat transfer out into the environment. The ground is having a stable temperature all year round. So if you want to have your house 20, you're just rejecting to that stable temperature, so that makes it more efficient. And if you install enough pipe in the ground, you can make this work in any location. So there's many places up in the far north where the area is very cold, and as long as you have enough loops in the ground, you're able to extract or inject the heat that you needed to heat or cool your building. These are just some more details of the refrigerant system, and noting some of the typical temperatures of the fluid when we're injecting into the ground. So when we're heating the building, we're injecting cold water into our ground loop, somewhere close to freezing, so we need to have an antifreeze inside of the ground loop. When we're trying to cool the building, we're going to put hot fluid into the ground, and it's going to come back a little bit cooler. In most locations, the ground temperature is going to be equal to the mean annual air temperature, somewhere 10 to 15. San Diego is a little bit warmer, around 20. So talking about energy piles, these are basically structures that serve two purposes. We're going to support the building, and we're also going to have heat exchange loops inside of them. These are closed loop pipes. Usually they're polyethylene plastic, so it's flexible. And one nice thing is that because you're inside of the building, you don't need to provide trenches to go below the frost depth. You need to have all of your heat exchange pipes at the surface, connected together in a manifold and routed through the building foundation to a mechanical room. These have all been studied for quite some time. I think the first applications were in the early 2000s in Austria. In the late 2000s, there started to become several research projects in the US, including one that I started at University of Colorado. Okay, so now going on to the research part of this presentation, I'm going to talk about these three different topics. The first, heat exchange using energy piles. I decided to put these technology readiness levels that the Department of Energy uses to classify different technologies. The reason I say that using energy piles for heat exchange is the past is because it's a mature technology. It has been demonstrated in field tests under real conditions, and it's been proven to work. There are companies that are designing these and building them as we speak. So that's why I call this a technology readiness level of 8. Thermal energy storage in soils, we've demonstrated this in field applications, but it still hasn't been used in commercial applications yet. So we're calling this technology readiness level 6. And for the future, this thermal improvement of soft clays, we're calling this technology readiness 4 because we've only looked at this in the laboratory environment. But also going from this application down, heat exchange systems, these are kind of using the heat as a resource, but it's also a waste. Heat storage, we're using heat only as a resource. And then improvement, this is both a resource and a tool. So how are we going to design ground source heat pumps and energy piles? I mentioned that you need to have a sufficient length of heat exchanger in the ground so that when you send heat pulses from your refrigerant loop, that they can be absorbed by the ground without changing the ground temperature. So this is the philosophy of heat exchange. Heat storage, you want the ground temperature to increase. You want to store the heat in the ground. But for heat exchange operation, we want to be able to send pulses of heat, and then they get distributed to the ground without causing the ground to heat up. We also want to avoid thermal overlap between other heat exchangers. And these are some different rules of thumb that you can use for preliminary designs of these systems. Usually you need about 150 meters of heat exchanger per thermal ton, and the thermal ton is the amount of energy you need to heat or cool a space. Energy piles are a little bit different than borehole heat exchangers because we're not going to make our piles longer to get more heat exchange capacity. The piles themselves are very expensive. The addition of the heat exchange tubing is only a fractional cost on top of that. So we're usually going to design the piles based on their structural requirements, and we're going to get the whatever length that we can have inside of the pile from that. So there's been some different studies on the configuration of the heat exchangers to get the maximum energy out of it, but I'm not going to talk very much about that here. There's many different studies that have been performed. Mostly analytical solutions are the first pass, but there's been a lot of work on thermal finite element or finite difference approaches for heat exchange. These are just some different references on the ranges of thermal conductivity that we're going to encounter. One of the limiting factors is this plastic pipe that has the lowest thermal conductivity out of the system. The fluid that is flowing through the pipe is, we need to have a fast enough flow rate that we have turbulent conditions, so we have good mixing. If we had laminar conditions, then you may have a stall out of the heat transfer across that fluid, so it needs to be mixing so that you evenly distribute the heat to the edges of the pipe, and then that gets distributed to the concrete in the surrounding soil. Soils usually have a pretty low thermal conductivity, and if they're dry, the thermal conductivity is lower than if they're saturated. One of the main ways that we quantify the system, as opposed to these individual components, is using a thermal response test. I'll show some results of these later. But in general, people found that the length to diameter ratio for an energy pile is relatively small, but they have high heat transfer, mainly due to the density of the materials and also just the geometric factor. So in these thermal response tests, you inject heat at a constant inlet temperature, and then you measure the outlet temperature as a function of time. And from that, you can figure out the system thermal conductivity. So the other thing that you need to think about is, yes, we're exchanging heat to and from the ground, but we're suddenly also going to have thermal expansion and contraction. And those are going to lead to thermal-induced displacements. And this is kind of the main thing that I was interested in when I started working on this. The tricky thing happens is that the restraint provided by the base, the toe restraint, and the building are going to prevent those displacements from happening. So if you prevent thermal displacements from happening, you convert them to stresses. So we want to make sure that any stresses that do occur are going to be within reasonable limits, capacity of the pile and the strength of the concrete. And if displacements do occur, we want to make sure that they don't cause structural or architectural damage. So these are just some schematics. We use different sign conventions than in structural engineering. We're using positive stresses for compression, positive strains mean contraction, and these are positive displacements are downwards. So if you're loading the pile from above using a contractile load, everything is positive, because that's the most common way that you're loading a foundation. When you heat the pile, it's going to heat about some point that depends on the boundary conditions. So I'll talk about that in a little bit, but we can represent the end restraint using a spring and the head restraint where your building is by another spring, and then some other springs on the sides to represent the shear stresses acting on the pile. So depending on all of those conditions, it's going to expand about some certain point, and that's going to be the point of zero displacement, and you'll have the maximum displacement at the ends. And when you cool the pile, it's going to contract towards that same location. We're going to call that the null point, so the point of zero displacement. So these are just some simple cartoons that we can use when we start to see the data to put this into context. If we have a floating pile, this is one without any end bearing, we apply a load to it, and it's going to be dissipated with depth. This is just a linear distribution in axial stress. When we heat it, it's going to expand about that point and add some additional compressive stress to the pile. And if we add the mechanical and thermal together, you get an increased compressive stress in the pile. You can also see that the upper part of the pile is going to be unloading, and the lower part of the pile is going to be loading even further. So if you're trying to do a load transfer analysis, you need to make sure that you know which direction each part of your pile is going. When we're loading the pile mechanically, usually everything is moving downwards, but now it's a little bit more complicated. During cooling, you have this opposite tensile stresses superimposed on top of your mechanical stresses. So one of the risks there is that you could potentially have tensile stresses in the base of the foundation. And that could be a risk for auger cast piles where maybe the base of the foundation is not reinforced. When we have realistic end-bearing restraints, it's going to change the shape of this stress profile. There's no restraint at the head and strong restraint at the toe. You're going to have this shape. Strong restraint at the head and none at the toe. It's going to have this shape. So we'll see this in some real data in a second. We have two different options to try to analyze those cartoons that I just showed. We can use coupled thermohydromechanical finite element analyses. These are good because you can interpret what's happening in the soil as well as in your pile, but it requires a lot of parameters and very advanced constitutive models. Validation can be very complex. So kind of the preferred method when you're redesigning these is the simple load transfer analysis using springs, nonlinear springs to represent the side shear and end bearing. Speaking of the effects of temperature on soils, I'm going to show some of these later in the presentation. We're going to have heat transfer from our concrete pile into the soil. And it depends on what type of soil we have, on what behavior we're going to obtain. If we have saturated soils, one thing that happens is that the water inside of the pores is going to expand 8 times more than the solid grains. So you can obtain this thing called thermal pressurization, especially in clay soils. And depending on the stress state, as those pore pressures dissipate, we could have thermal contraction. There's also some changes in the yield stress of the soil. When we heat it, usually the yield stress decreases. That causes thermal softening, especially in overconsolidated soils. But this volume change due to the outflow of water in normally consolidated soils causes hardening and an increase in shear strength. So in the last example that I'm going to show you, I'm going to focus on these normally consolidated soils. And we're going to see when we heat them, it causes contraction and an increase in shear strength. So this is kind of different than you'd expect for concrete or steel. When you heat them, they're always going to expand. But soils, depending on their stress state, they could contract. Kind of a weird behavior. Sands are usually pretty inert. They're going to expand and contract, but there have been some studies showing that ratcheting could be an effect, that every heating and cooling cycle, you're going to get some continued movement. Unsaturated soils are very complicated because when you heat them, you're going to cause phase change, and water is going to flow away from your heat source. That's going to be called thermally induced drying. That is going to lead to an increase in suction and an increase in shear strength. You're still going to see a softening effect, but the increase in shear strength is greater than the softening that we see. So I'll also show some examples of some tests where we observed that. This is just an example of thermal THM finite element analysis. In addition to these couple processes that have many parameters, we need to have soil pile interface characteristics, which anybody who's worked with piles knows that those are very tricky to obtain, and the disturbance during installation really makes them difficult to predict without doing a load test. However, there's been many studies using finite elements. I just list them here in case you're interested in reading about these later. I'm going to show some results of load transfer analysis instead, where we represent our pile with a set of linear springs, and then nonlinear springs at the toe and along the sides. One of the tricks here is that we need to input the ultimate pile capacity, which could be affected by temperature. The nice thing about these load transfer analyses, it's going to give us our predicted load settlement curve if we do a mechanical loading test. It's going to tell us about our mobilized side shear, and it's going to tell us about the stress and strain distribution within the pile. And hopefully if we validate these enough with data, we can be using this readily in design. We need to think about the effects of drainage during mechanical loading. Is it going to be an undrained material or a drained material? So we have a choice for undrained or drained. And then we need to think about the strengths that are going inside of those, the effects of temperature on the shear strength before the mechanical loading occurs. These are typical TZ curves. These are measured. In our studies, we usually use a simplified hyperbolic model. But because the top half of the pile is unloading and the lower half is loading, we need to make sure that we have a unloading path in our model. Most of the TZ analysis is just focused on loading, so we just had to add an additional feature for that. And this is the end bearing curve. I'll show some techniques that we can use in the field to try to predict that. Mechanical loading, these are easy. You usually apply a displacement at the toe and then iterate until we reach equilibrium. And that'll get, you apply the displacement at the toe and you can figure out what the load is at the top and go from there. When we do the thermal load transfer analysis, the interesting thing is that we need to have an additional spring at the head of the pile. And then we also have this concept of the null point, which is a point where there's no displacement. So different from the mechanical place where we apply a known displacement to the toe, we need to first make a guess at what that null point is, and then start to apply displacements from that point, thermal expansion from that point. This is just a very simple case where we have no side shear on the sides of the pile, but we have springs on the toe and the head. And if you heat the pile, it's going to expand by alpha delta T. So alpha is usually around 10 microstrain per C. And we can just use equilibrium of the pile to figure out the location of that null point. It's going to depend on the stiffnesses of those two springs. When we have the side shear, it makes things much more complicated. So we need to guess where the null point is, start with initial values from our mechanical TZ analysis, and apply an alpha delta T for each element. Alpha delta T is the amount that the pile would expand freely if it was not restrained, but it is going to be restrained by side shear. So that we need to adjust that until we actually find out the actual amount of thermal strain. So if there's no restraints at all, the entire pile would just expand by alpha delta T. If there is restraint, it's going to be less than that. So we can go through some different examples. I will show some comparisons with field data later, but these are examples for a floating energy pile where there's no restraint to the toe, a pure end-bearing pile where there's no side shear, and then a semi-floating energy pile, which is probably most realistic what we would expect. So high stresses at the head and low stresses at the toe. Okay, going on to a couple of the case histories. The first one is a shower shave facility that was constructed at the U.S. Air Force Academy. I worked on this with Professor Karen Henry there. And an interesting thing about this project, it was a one-story building. It didn't need to be on deep foundations, but as part of our project, they were able to add these foundations to their scope. I always joke that this is the strongest bathroom in the world. So if you want to visit, it's still there. So we had a series of 8 15-meter energy piles around the perimeter of the pile. The Air Force Academy has an interesting program where they, before they've taken any classes, they go out to this place called FERL, the Field Emergency Engineering Readiness Laboratory, and they build things, retaining walls, excavations. They see how it works, and then they go back to the classroom and learn. So we gave them a nice bathroom that is warm, I hope. The area there is mostly sandstone. There's a little bit of sandy soil near the surface, but majority sandstone. We used a dry hole approach for the drill shaft construction. I found out after we installed them that these were installed by a water well installer instead of a drilled shaft installer. So the water well installers just want to go deeper than their required depth. So this driller drilled past our 15-meter limit and left the loose material at the toe of the pile. So basically he drilled down and then there was loose sand at the toe of the pile. In the normal dry hole approach, you're going to make sure that you have a nice flat material at the base. We didn't need this for the capacity of the foundation, but it added some complexity when we looked at the results later on. So here's the layout. 2 of the piles have instrumentation off to the sides, and piles 4, 3, and 1 have strain gauges throughout their depth. These were 24-inch diameter piles, so they're relatively narrow, but you can see the pipes on the inside of the reinforcement cage. One of them we were looking at as a retrofit, where you would maybe core down through your pile and install a vertical heat exchanger into the middle. So to replicate that, we just had a pipe in the center of the pile that we inserted the tube in later. After we had these pipes attached, we pressurized them with water and had a valve at the top, and we could use that as a way to detect if there was any leaks during the construction process. Then we needed to pick these 50 feet by 2 foot reinforcement cages up. So we did that successfully without damaging any of our strain gauge sensors. And we lowered that into the hole. And you can see the dry hole here, and we tremmied concrete up from the base. You can see that they're still under pressure, which was good. We didn't have any damage. And then we brought all of the pipes into our mechanical room. This picture saved me a lot of time at one point because all of the pipes came in from different locations and they didn't come in the right order, 1 through 8. So thankfully I knew where each thing was located so I could send the water in the right location after we poured concrete into all of this. So we made a nice mechanical manifold where we had heat going in one side and then the cold fluid coming out the other. We did some simple thermal response tests where we had a pump that circulated hot water through the pile, and we measured the temperature and flow rate going in and out. And then we had our vibrating wire strain gauges at different locations along the pile. One tricky thing with these is that temperature causes, they work by like a guitar string. So you have a magnet that plucks the string. When you heat it, that string actually expands. So if you don't process the data correctly, it makes it look like your pile is contracting, even though it's expanding. But if you do these thermal corrections properly, you can see that the pile is indeed expanding. This is what it looked like afterwards. We had a 3-foot grade beam, which added to the strength. And then we waited some time for the concrete to cure. We were able to get the temperature profile at the site over the seasons, and the temperature, the strains during curing. And then you can see that the mechanical load due to the self-weight of the building was absorbed in the first 2 meters of the foundations. So we didn't really need to have deep foundations to support that load, but that's okay. So these are the 3 foundations that had strain gauges in them. I have some papers looking at the details of the corner and interior piles. I'm not going to talk about that today. We did our thermal response tests where we had a constant flow rate. Temperatures of the piles increased, and then the difference between the temperature inlet and outlet tells you the heat flux into the pile. Then we can look at the temperatures of the pile themselves. They're generally pretty uniform with depth, except near the surface. And then these are the strains that were measured. These are definitely much less uniform with strain than the temperature. So the temperature is relatively constant with depth, but the strains are variable. And this is due to the soil structure interaction. The next thing we looked at are these mobilized coefficients of thermal expansion. Everything is linear, which is good. And if it was able to expand freely, it would have a coefficient of thermal expansion of about 12. So in the center of the pile was where the most restraint was located. We expected that the toe would have more restraint, but because of that loose material due to the construction technique that the contractor used, it was softer than we expected. We expected that this would go down. So we chose different times where we had different constant temperatures, got our strains from those, and then we could convert those to stress using this equation. So you can't use Young's law to get Young's modulus to get that, or Hooke's law. We need to look at the difference between the actual thermal strain and the free expansion strain, and then multiply that difference in strain by the Young's modulus. And that gives us our thermal axial stress. So using that approach, we found that our thermally induced stress was 5 MPa. That's more than the mechanical stress applied by the foundation. So that's something that we need to think about to make sure that those induced stresses are less than the capacity of the concrete. But the compressive strength of concrete is 20, so we're well below that. Assuming that the toe was fixed, which wasn't really the case, we could integrate the strains with depth and obtain the relative displacement. So we got somewhere 1.5 millimeters of upward expansion during heating. Just looking at some different angular distortions from the literature, if one of those was heating and all the rest were not heating, that would be your case where you'd have the most angular distortion. So the change in height over the span between the 2 piles, we were getting 1/6,000. So that's way less than would cause damage to a masonry building. So the amounts of thermal expansion and contraction that we're going to get are pretty small. The stresses induced could be high. We wanted to simulate these then with our load transfer analysis I told you about. So we had a special device that we lowered down in the hole. It's similar to the handy borehole shear test. Expanded this against the side of the pile and pulled up. And we were able to get these TZ curves for different temperatures and normal stresses, and temperature had a negligible effect. And we were able to then match these with our measured values, and we got good results. We did have to calibrate the pile, the springs at the head and the toe. We didn't know those a priori, but from the side shear, we got a good response. The second case history, this one's a little bit shorter. This was a building that was being constructed in 2010 in downtown Denver. They were already installing a conventional geothermal system, and they said, oh, do you want to come in and install a couple energy piles? So we quickly bought some sensors and came out there and tagged them onto the project. They had 40 conventional geothermal boreholes. This is kind of noting to get the heat necessary to heat and cool the building, boreholes needed to be 470 feet deep. So our energy piles were, again, about 15 meters long. So we're not going to increase the foundations of the building to 470 feet to meet the heating demand. We're just going to carry the structural demand. This is the building footprint. We chose 2 different piles, A and B, to become energy piles, and we had to route the tubing over to the mechanical room here. These are larger diameter, about 1 meter diameter, and they go through this Denver blue shale, which we found was an interesting material that was sensitive to temperature. So these are just the operations of the energy pile with time. We looked at the heat transfer, and we got about 91 watts per meter, which is consistent with what I showed you in that graph before. These are the temperatures over time. It follows kind of roughly sinusoidal trend. My graduate student forgot to reconnect the data acquisition system on a few different occasions, which gave me some heart attacks at the time, but you can still see the trend if you look at it carefully. So even though the temperatures follow the sinusoidal trend, the strains are kind of tending upward. And that was a little bit scary to us, that things are moving in this direction. And we attributed that to thermal drag down, so that the claystone there was maybe sensitive to temperature, and we superimposed an additional downward mechanical stress on top of the pile that increased from season to season. But even then, our mechanical load, this one has a 5-story building on top of it. In addition to the heating and cooling, we're still only around 12 MPa. So we're still within the limits of the stresses. And in this case, we're having both heating and cooling, so we can have contraction and expansion, but we're still within that 1 to 1.5 millimeters of displacement. Before I talk about the other two applications, I just wanted to note about thermal energy as a waste. There's been some studies that, like regional scale studies, if everybody were to adopt heating and cooling, you could have some locations in cities that become hotter than others. These are residential areas and commercial areas. So that could be a risk. If you use a district heating system for our geothermal, we could potentially transfer that heat from one place to another. And there's been a lot of work by Alessandro Radaloria at Northwestern looking at heat island effects in the Chicago area and potential thermal deformations. So I won't go into detail about that, but these are areas that you may need to watch out for. So the second topic is the storage of thermal energy in the subsurface. We had a project where we were looking at collecting heat from solar thermal panels and injecting that into the subsurface, and in particular into unsaturated soil layers. Most of the US has abundant solar thermal energy. However, it's only available during the day and usually only in the summer. So we need a storage system that we can use to access that heat in the winter. These locations in Denmark and Canada, they're very far north, they're very cold regions. They have 98% efficiency using these approaches. So the way that these approaches work is you have a set of closely spaced boreholes, and in our case, we're going to also have closely spaced energy piles, and you inject heat into the center of the system under high temperatures up to 90 Celsius, so much higher than those temperatures that we encountered during heat exchange, which are around 35 Celsius. Wait some time during the fall, and then extract heat during the winter to heat your building. In the locations that have been studied in Denmark and Canada, they were in places where the water table was very high, and there was actually groundwater flow that was taking the heat away with it. So we have advocated installing these into the unsaturated soil, the Vedo zone above the water table. One nice thing is that there's less potential for groundwater flow, and the soil has lower thermal conductivity, so there's more heat storage. However, you need to consider other mechanisms of heat transfer, phase change, and then vapor flow. Because this is very complicated to study in the field, we have looked at this using boreholes in the field. We've kind of mainly been focusing on centrifuge tests. So this was a study that I performed when I was at University of Colorado. We wanted to look at the effect of heating on an energy pile in unsaturated soil on its strain distribution and also its ultimate capacity. So in this case, we have a tank with an energy pile in the middle of it. And the reason that we like to use centrifuge modeling is that we can scale the stress state. So we can have a reduced scale model that has the same stress state as in the field as in the prototype. And we can scale things like time and other variables to have similitude between the two. So this is our scale model energy pile that we looked at for the unsaturated soil tests. This is reinforced concrete with chicken wire and different strain gauges, which is pretty tricky to build. And we had a heating unit that went through some slip ring stacks down through our energy pile in the centrifuge, spinning around at 40 Gs. And then we made measurements. So we heated the pile to different temperatures while the pile was under a seating load, and then we loaded it to failure. So that's something that is hard to do for an energy pile in the field, but it's easy for us to do in the centrifuge. First, we did tests on sand. We heated the pile to different temperatures, measured the load settlement curve, and there was no effective temperature. Then we did the same thing on unsaturated silt. We saw that the hotter the soil was, the higher our capacity was. We attributed this to thermally induced water flow away from the pile, which led to an increase in effective stress and interface shear strength. And this was the case when we measured it using different sensors located at different locations from the pile. As the soil became hotter, it became drier. These measurements are nice, but you can't have a measurement right at the pile interfaces, which is what we need to do a load transfer analysis. So we need to complement that with modeling. So here we went down to COMSOL and looked at a heat transfer model that was coupled with liquid flow, gas flow, and phase change. And this is a non-equilibrium phase change model, so it's very complicated. We needed to calibrate that using some different parameters for unsaturated soils. And we also needed to calibrate the phase change rate and the effective diffusion coefficient using some tank tests. So we did all these in support of trying to simulate what happened in the centrifuge test. But with that, we could simulate the temperature distribution and the volumetric water content distribution. These are our measurements from the test, and we had pretty good match with those. And as you see, when you heat the soil by 10, by 18, it causes the water content to decrease right at the pile interface, and that causes the effective stress to significantly increase right at the pile interface. I'm a big advocate of using effective stress for unsaturated soils because you can consider both suction effects as well as degree of saturation effects. So now that we know that the effective stress is increasing at the pile interface during heating, we can put that into a load transfer ultimate capacity analysis, and we were able to get very good predictions of our ultimate capacity as the pile is heated. So with this case, we're proposing that when we use heat to store, when we store heat in energy pile arrays, we're able to not only increase the temperature and store heat, we can also increase the capacity of our piles. We've also done some simulations where we have a group of energy piles and we heat it and cool it over several seasons to see how this is affecting the behavior of the soil. And this leads to large increases in temperature in the region of the pile and also decreases in temperature and degree of saturation around the pile. And over time, usually the efficiency is going to increase. Whenever you're doing borehole thermal energy storage, there's always going to be losses into the outside of your array just due to natural conduction. But when you extract heat, you're never going to extract all of it. So the next season, when you inject heat, it's going to be a little bit more efficient. In this case, we show the saturated case being the most efficient, but you have to also note that if you have saturated soils, there's usually going to be groundwater flow. So this would only be the case where the saturated soil will be statically there without any groundwater flow. Okay, so the last topic that I want to touch on is kind of the future, using this thermal energy, which could be waste heat, but also from other sources, to improve soils. So in this case, the thing we're going to try to do is heat our energy pile in the ground and keep the temperature constant for a certain duration of time. While the soil is being heated, it's going to increase in pressure due to this differential thermal expansion. And we've done some studies that show the deeper you go in the soil profile, the higher your pore pressure is going to be. And initially, you're going to have some thermal expansion when the soil is completely undrained. But as these pore pressures dissipate and move away to other regions, you're going to have thermal contraction. And that thermal contraction is going to lead to a decrease in void ratio and an increase in shear strength. So we've proven this with some different thermal triaxial tests, where we do the shear strength at room temperature, heat it and measure the shear strength when it's hot, and then cool it to measure the shear strength when it's cold. And in all cases, we saw that this heating cooling cycle led to an increase in the shear strength of the soil, undrained shear strength of the saturated soil in this case. So we again went to the centrifuge to try to prove this. We had an energy pile in saturated kaolinite clay. We had different sensors around the pile to measure water pressure and temperature, and a device to measure the undrained shear strength profile using a T-bar. This is the UCSD centrifuge in this case. So we spin the centrifuge up, install the pile, heat it, wait for these processes to happen, and then pull it out to measure the pull-out strength. So I'll get to the results right away. The higher the temperature that we apply to the soil and go through this thermal improvement, the higher our capacity. And our capacity could increase by almost 120%. This was very repeatable for different pile types, different head restraint types. So we're very pleased with the results there. But we want to be able to predict those increases in capacity. So the first thing we did is we measured the shear strength profiles before and after heating. So these are during penetration and pullout, and also during the insulation of the pile, we can get the undrained shear strength of the soft clay. And we found that the undrained shear strength is very sensitive to the void ratio in the soil. And the higher the temperature we apply, the greater the shear strength increase will be. We have more of an increase in shear strength near the soil surface than deeper in the profile. So then we needed to predict the change in temperature of the soil around the pile. So we used an analytical solution to the heat conduction equation and obtained these different profiles. We wanted to heat the soil within a target zone around the pile that was going to be affecting the capacity. Our T-bar location is located outside of that target zone, but if we see improvement at the T-bar location, it means that we're also having improvement near the target zone. So the first thing we did is we used some thermal pressurization techniques. These were developed by Mitchell back in the 70s. We kind of enhanced them a little bit more to add to better estimate the parameters going into these models. And if we know what the change in pressure is in the soil due to a change in temperature, we can estimate the amount of water that's going to flow out. And if we know the amount of water that's going to flow out, we can look at the change of void ratio. So this is our pore pressure equation, measured versus predicted. We got a pretty good prediction there. And then we know that if we have a change in void ratio, we should also have a change in undrained shear strength. So we used the ChemClay model we have a normally consolidated soil in this case, to obtain the undrained shear strength as a function of void ratio at failure. And you can see that our measurements from our T-bar tests match up well with that model, with a correction factor to account for overconsolidation ratio and stress-induced anisotropy differences. But then we could take that shear strength and put it into our alpha capacity model, and we were able to get a very good prediction of our pullout capacity. So I think that that was a positive trend at the end, that we can use heat as a tool to improve the pullout capacity of these piles. So just another comment on the future. There's a lot of different types of energy piles that we can look at. I've worked with Ji Wang from UT San Antonio. We're trying to develop some helical anchors that are filled with pressurized CO2 to obtain a natural thermal siphon. So in this case, we don't need to have a closed loop heat exchanger. You're just going to have phase change of the CO2 as it absorbs heat from the ground, evaporates and condenses, and goes in a cycle. We're also looking at piles in offshore situations, namely these torpedo piles that you would drop down in deep water depths to penetrate into the soil. One of the problems with torpedo piles is you can't increase their size beyond about 22 meters in length because of the vessel requirements. But if you can increase their capacity by 10%, it can have major effects on the behavior of these floating platforms. So we're looking into thermal improvement of these torpedo piles. And finally, my recently graduated student, Radhavi, was looking at thermal drains. So these would be maybe porous piles that you would install in the ground. And instead of having the pressurization of the water that would cause water to flow away, water would actually also flow into the drains themselves. So I think there's a lot of things that we can look at in the future to design energy piles in different ways. So I know I went through a lot of different topics, but hopefully I demonstrated to you that energy piles are a tried and true technique for heat transfer and building support. There are going to be thermally induced stresses and displacements. We know how to quantify those. We need to make sure they're within limits, but we feel confident that we can do that for different projects. We always need to think about the effects of heat exchange on soil behavior. When we're having these challenging soil deposits like this clay stone, making sure we have things like don't have drag down effects. And we want to make sure that changes of capacity or deformation don't affect the stability, but also we don't want to affect the efficiency of the system. And I think there's a lot of opportunities to use energy piles in different ways to achieve thermal soil improvement, but maybe also environmental enhancement in the long run. So a lot of students have worked on this. I'm very grateful for their hard work, and also support from National Science Foundation was critical in getting this done. So yeah, thank you very much for your attention.
So we made some questions.
I got one question. Is the thermal is of expansion and contraction, does this thermal energy can affect the life of the pot due to the fatigue failure or nocturnal?
Yeah. Yeah, I think usually fatigue happens when the strains are above a certain level, but the strains if you look at free expansion strain, alpha times delta T of a normal length of a pile, they're still going to be very small compared to the ones that are going to cause fatigue failure. I think there was a student in Switzerland that was studying that topic, and they found that it was okay.
What would be the relative cost increase associated with implementing this on a, let's say, just a hospital type program?
So materials-wise, very small, 1%. Plastic pipe is relatively inexpensive, but the bigger challenge is that your architect needs to want to use heat pumps as the main heat transfer mechanism, and then the construction is different than maybe how we usually do it for buildings. The mechanical contractor needs to be involved at the same time as the foundation contractor. They need to work together to install these pipes, and once the foundation is set, they need to route these over to the mechanical room before the next set of trades comes along. So they're
Like maybe 2 to 3% increase?
yeah, and as long as there's good planning amongst the team of people building the building. But there are some companies that are specialized on adding this as a feature. So Endowed Energy in New York is one of the specialists on this. They do the analysis and then support the additional design details that need to be considered.
Do you think the repeated expansion and contraction will affect the site friction on the pile long term?
I would say it depends on the amount of load that is applied on the pile. So if you're very close to the capacity of the pile, like 70 or 80%, you could start having ratcheting effects. But usually we oversize the capacity of the pile compared to the loads that are being applied to it. There were some interesting studies in Hong Kong where they had very heavily loaded piles in clay, and as you heat them, they would slowly ratchet down into the soil. So,
in one of your graphs, you showed an increase of about 40 degrees Celsius, and it looked like you were going maybe 2-3 pile diameters away. How long does it take for that heat, basically to heat up to 40 degrees?
for in the centrifuge test?
Yes. No, in real life, you have, let's say, a 3 feet diameter.
But for the thermal consolidation case?
Yeah.
Yeah, we looked at the time scaling on that because heat transfer is the same at 1G, and in the centrifuge, the gravity has no effect on the heat transfer. But you can scale the time, the diffusion time. So if you scale that time, it would be close to a year of heating. So you would need about a year in order to have this pressurization, dissipation. So you need a sustained heating source during that time.
Do you think there's any opportunity to utilize this technology in curing concrete? We had
Yeah.
Hilton Tower where they had plenty of sensors. Maybe you could use for that.
Yes, for sure. And there have been people thinking about that. We thankfully just left the sensors on when we were, we installed all these temperature sensors and then the concrete cured. We weren't necessarily trying to modify it, but we were able to see that there are stresses induced by the curing process. And you could easily, if you were anticipating it, change the temperature of the pile to reach that. Usually you can have a uniform temperature with depth during heat circulation.
Hey, Joe, I have a question. It's a little bit related to Daniel's question, but I'll phrase it a little more generally. In general, and let's talk about heating thermal piles, not storage or improvement. But in general, would you rather have a sandy, permeable site, or would you rather have a clay site? Would you rather have a high groundwater table or a low groundwater table for one of these projects to be effective?
So if I was just doing heat exchange,
Yeah.
I would want as high of thermal conductivity to the ground as possible, so that the thermal conductivity is high and then the heat goes away.
That makes sense.
Yes, you send the pulse and it, yeah,
So a sandy
dissipates.
site then with a high groundwater table. would
Yes.
be preferred.
Yeah. Yeah, depends on what you're doing.
Right, exactly.
But yes.
There's any restriction for the diameter of pile, certain pile, maybe more different how you do it.
I think in that band of the length to diameter ratios that people studied, it didn't have a huge effect for the different types of piles. I think most piles are in the 3-foot diameter range, and yeah. So the more area you have in contact with the soil, the better heat transfer you're going to have. So there are geometric effects. Yes.
Are you concerned about the possible difference if there is any high fault area?
So that's a good question. But if I didn't really highlight it, but oops, I stopped the screen sharing. There, you don't put refrigerant into the ground.
Where you see notes?
Okay. Yes. So you're never injecting the refrigerant into the ground. There's a coil right at this interface here that is shown in this picture. So in that coil, the water is on the inside, and then the refrigerant is going through the outside. So the refrigerant is just staying within this loop, and then your water with some antifreeze inside of it is in the ground loop. Yeah. Yeah, it's propylene glycol, but not a huge percentage because it decreases your efficiency.
Is the heat pump technology something readily available in the market? Is there any sort of specialized equipment?
No, because the geothermal industry has been active since the 60s, so the units are pretty commonly used. My mom has them in her house in North Dakota. They have the same maintenance issues as furnaces do. I had to buy a new furnace. So I think they're heavily computerized, so you can track a lot of their performance as well.
One more question. Almost like a power cooling, in the pile, that's the water tank. How often you have to do the food check for a year? Maintenance.
So you definitely wouldn't have access anywhere here on this part. Refrigerant leaks over time, but that's all within the mechanical room. You can always pressurize the fluid that's within your pipes. And as long as you make sure that there's no damage during the installation, we use plastic pipes in landfills, and they have very good durability and long lifetimes. So I think in a pipe in an isolated place where there's no UV degradation, the pipe will be pretty stable. Cool. Thank you.